So let's look at what you would see on a test, which are more mixed examples, and how we know what we're supposed to do when. So let's take a look. A manager must select 5 delivery locations from 9 that are available. Find the number of different possible routes. So we're making an order or a route out of things, which means we're going to use something where order matters. We talked about where order matters and where order doesn't matter. We said that order does not matter if you are a combination. So order does matter if you are either using the fundamental counting principle or permutations. You just have to be careful if you're going to use one of those, that if you're going to decide to use permutations, you cannot repeat yourself. So in this particular one, because we're trying to make an order or route, we're going to use either fundamental counting principle or permutations. Now, because we're doing delivery locations, we're going to assume we're not going to go to the same delivery place twice, so we're not going to repeat ourselves anyway, so we can use permutations. Now, how many different places am I going to look at for total for my deliveries is 9. So I'm going to start out with my total of 9 locations. And of those 9 locations, how many am I going to make my route up with? I'm only going to use 5 of the 9. So that will be of 9P5. Or we can still do fundamental counting principle. It's that we're making a route of 5 places. Be careful. You're starting out with, I have 9 to choose from. Then I would go down to 8, then 7, then 6, then 5. Either way, you'll get the same answer. What do you get? You get the value 15,120. Here's another one. What is the probability of randomly generating 16 digits and getting your credit card number? Well, first of all, let's talk about credit card numbers. Does order matter? So remember, this should always be our first thought to determine what we're going to do. Does order matter? And the quickest way that I would start would say, if I had a credit card starting in 5242, or swap it around 2425, are those that, can they be considered the same card? Absolutely not. They are completely different. So does order matter? Yes. These two are not the same. If you flip them around, it's not the same card. So that means we need to either use fundamental counting principle or permutations. Big catch here, and I can see it in my example, is credit cards can do what? See the 2 2s? We can repeat, which means I have to use the fundamental counting principle. So the idea would be I have 1, 2, 3, 4, 5, 6, keep on going, 16 slots to fill in. And what would I have for each of those 16 slots is I'd have a choice of how many numbers? Well, anything from 0 to 9, which is a total of 10 numbers to choose from. So I'd have 10 numbers to choose from in each of the 16 slots. So the quickest way to kind of write this out would be 10 to the 16th power. That is crazy large. 10 to the 16th power means you'd have a 1 with 16 zeros behind it. So let's just leave that as 10 to the 16th. However, that is still not what they were asking for. They ask, what is the probability of somebody randomly guessing your credit card? Well, they'd actually have to get every single number on your credit card right, and there's only one credit card like that. Well, that'd be 1 over your 10 to the 16th. So your chances of somebody randomly guessing your credit card are pretty much zilch. And that's not even taking into account that whenever you use a credit card, you need a CVV code usually, or at least a zip code, which is going to make this even less likely. So we're going to leave our probability just like this, and that is good enough. 1 out of 10 to the 16th power. Now let's take a look at this next one. Receipts often show the last 4 digits of a credit card number. If those last 4 digits of your card are known, what is the probability of randomly generating the other digits of your card? Well, we know that a credit card order does matter. We just did that in the last part. Normally has 16 digits. Now, we're saying that 4 of the digits are known. Because usually when you get a receipt, you do get the last 4 digits. That still leaves you with 12 unknown digits that we're worried about. Okay, so the only digits we're worried about is the first 12. So instead of being 10 to the 16th like the last time, we have choices of 10 to the 12th this time, because I've only got 12 of the numbers I don't know, but they could still be any of the 10 numbers. So what's their probability of guessing these 12? Still like the same one. There's only going to be one like that. So the idea is that they're going to choose 1 out of those 10 to the 12th options. It is quite a bit better, but it's still very much slim to none. That's why companies are not concerned about just giving you a receipt with the last 4 digits, because it still is very, 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 very unlikely for them to guess your credit card number. In this next problem, we're looking at something that would be more of a science example. It says each nucleotide can contain either adenine, guanine, cytosine, or thymine. We want to form linear triplets. Triplets assumes that you're choosing how many at a time? You're choosing 3. So you want to form linear triplets using the 4 nucleotides. So you're going to choose a group of 3. So order will matter, and the question is, how many different possibilities are there if you can choose any? It says all 4 of the bases can be chosen for each component, meaning you can repeat yourself, which is why we've already got it set up for fundamental counting rule or principle. It's the only one that allows us to repeat and still puts things in order. So for my first slot in my triplet, I have my adenine, my guanine, my cytosine, or my thymine, all 4 to choose from. And for my second component, it still says I can use all 4, so still have 4 to choose from. And for my third part of my triplet, I still have 4 to choose from. So it's 4 times 4 times 4, or I can do just 4 to the third. Either way, I get 64 different ways to come up with different genetic triplets.